function. Okay, so we have this. Okay, so the function of point of this constant scheme is given by that. Okay, so these are the locally constant functions. And on the other hand, what are so this is for more inputs. On the other hand, for any scheme H over S. So what is from S schemes of MS into H? Well, so this is the sum of the things. So for each copy, we have to choose a morphism. And so in fact, this is a product for all M in M of from S of S into H. And so this is just the product. And so this, so the right-hand side, this is just a set of S points of H. Okay, so we have this second formula here. And well, and this is all this is functorial. That is, if U from M to N is a map of sets, then of course we get a map from MS to NS. And a further property of this construction is that further, if we make the fiber product of S of two constant schemes like this, so this is naturally isomorphic to that one. Okay. So this commute with products. And so in particular, if N is equal to M is a group, then we get so we have this natural identification. And the multiplication of M induces a map like that. And so we get the composite. So MS is a S group scheme. So we have a functor, hence we have a functor from the category of groups to that of S group scheme. Let me just, which takes a group M to the group MS. And we can, so let me call this for the moment formula 1. And let us call this formula 2. And formula 2 generalizes. So 2 gives, for obvious reasons, that if M is a group, H S group scheme, then we have so now if we look at the homomorphism of S group scheme into H, Yeah, so maybe so this is just a product. So for each m, we have to give an element here. So I can also write this as a hom. So this is the same thing as hom in the category of sets from M into H of S. For each M, we have to pick a section F of S. And so if we consider inside this set, those morphism of schemes, which are morphism of group schemes, so we find on the right-hand side, so this is just a set of morphism of groups from M into the set of S points of H. So we have this property, and maybe we call this 3 for the sake of it. Okay, and now I want to digress a little. Well, it's a digression because we don't need the full generality of the definition, but it's useful to give it anyway. So let GH be S group schemes. So let's define a functor. Let's define a functor.
In the last equation, do you assume S connected?
I'm sorry, I didn't.
In the last equation, do you assume S connected?
No.
No? Okay. Okay.
No, I don't. No, we don't need S connected because.
No, I meant in the last equation, on the last, this one that you just wrote.
The number 3?
Number 2. The final equation that you just wrote. No, here. Home S groups MSH.
Yeah, no, I don't need it's just the same as that one. I don't need S connected here.
Okay, thank you. Okay, thank you.
Yeah, so let's define a functor which will write hom S group underlined of of G into H. So it's a functor from the category of schemes over S to the category of sets. And it takes every scheme T to the set of homomorphism of T groups from GT from HT. Okay, so this is a functor, a contravariant functor. And so this looks very abstract, but we will have to consider this kind of thing later. We want to prove that two group schemes become etale or become isomorphic after some base change. So one fancy way to do this is consider this functor, prove that it is representable by some etale scheme. And then if you take a point in that etale scheme, then you get an isomorphism. So this is why we will need this in this generality. For the moment, we will not need this. And from the definition, it's clear that this commutes with base change. That is what I mean by this. So if we take this functor, and if we base change it to some scheme over S, so this is the same as the functor. Sorry, I forgot to write group. So this is the same as base changing G and T to T, G and H to T, and taking the same functor. Okay, so this follows from the definition. So this is just a functor to the category of set, but further, if H is commutative, then each set from T group of GT H is a group with law induced by that of H. Hence we get a functor, hence we get a group functor so in this case, so this is a functor from the category of schemes over S to the category of groups. Okay. Okay, of course, the point is that if so, so if you write the group row of H additively, so you just add two homomorphisms by adding the values, but this is a homomorphism. So if H is commutative, this is a homomorphism. Otherwise, it need not be a homomorphism. So it's good to take H commutative. And now we consider the case of interest for the moment. Yes? Yes, I'm sorry, yeah. Yeah, so the right side H should be commutative. So now the case with, so now we take H to be the commutative group GM over S, and for any S group G, we set T of G. This is a Hom S group of G into GMS. Okay, and so let me just record that. So this implies, so this function commutes with base change. So that is, if we base change this, so this is the same as T of G. Okay, but so this is, maybe this is a little bit confusing because I'm using D of G and we have already used D of M previously, but actually the two things are the same because, an important remark. So from now on, let M be a finitely generated abelian group. And so the D, let me write it, the diagonalizable group the MS, so was defined. Was defined earlier. And we saw that for any scheme T over S, so we saw that the value, the T points of these diagonalizable groups, so we saw that this is just Hom groups of M into the invertible functions of T, but so this is the same as Hom groups. So the right-hand side is just the functor GMT evaluated at T, and by this formula, so we see that this is just from this is just the same thing as the morphism of T groups from the constant group MT into GMT. And so this is, by definition, so this is the same as so this is D of MS evaluated at T. Because if we plug in here MS, so this is just MS into this, and so this is just MT into G. Okay. So the notation is coherent. So this more general definition agrees with the former one. Okay, so we have this this object. So the group, the diagonalizable group that we defined earlier is the same as the dual of the constant group MS. So we have this, and so this is also compatible with this general notation for base change. Okay, so why are we doing all this? Well, one may wonder why making complicating it something that was simple. So the reason will come with the next theorem, which is called the biduality theorem. So the reason is that, oops. Well, the reason is that we are going to, well, let me give the biduality theorem. Okay, so now let's proceed towards the important biduality theorem. Okay, so as usual, M is as usual. I will not repeat it, but M will always denote a finitely generated abelian group. I'm sorry, I didn't get it. Yeah. Yes. Yeah. No, no. This is always true for any m, but for the interesting theorems, as we will see later, it's important to have m finitely generated for well at some places. But for the moment, all this is completely general. Okay, so what happens if we consider? Oh, I didn't say it, but so D of G is called the dual group of G. Okay, so we start with M. So we consider the diagonalizable group D of MS. And what happens if we consider it's dual again? So the t-valued points, so by definition, this is all the morphism of t-group schemes from D of M T into G M T. And everything here is affine. So this is the same thing as all the morphism of Hopf algebras. So GMT correspond to this OT algebra, and the other group corresponds to the group algebra of M over the structure sheaf of T. And here, of course, the multiplication is says delta X is X times X, and the antipode of X is 1. Okay, and so we have to find all this morphism of Hopf algebras, and we have a natural map. We have a natural map from the group M itself into this, which is given as follows. So that one is given as follows. Let me write. On the other hand, what is this? So we saw these are just locally constant functions from T to N. And so we have a map in that direction. So given phi from T to M, locally constant. So this gives a partition of the topological space of T. It's a disjoint union for all M over M of some subset Tm, where Tm is a set of those T in T, such that phi of T is M. And each is open, each is open and closed. So each is open because the function is locally constant, and each is a complement of the other, so it is also closed. Okay, and so on each. So let me write Kloppen to me, so that they are closed and open subscheme. So on each of these subscheme, we have the map. We have the Hopf algebra map given by x goes to m. Okay, so any algebra map is defined by the value of x, and if we send x to m, so this is a Hopf algebra map because they both satisfy the same rule with respect to the commultiplication of augmentation. Okay, so there is a natural, and of course this map is injective. So we have a natural inclusion of ms of t into this, and the theorem is that this is an equality in fact. Yep. Mm-hmm. What here?
Yeah, the right-hand side.
This?
OTM, what happened to the dual?
Okay, so both
No,
schemes
to the
they are
right-hand side.
here.
Yeah,
Yeah, this is what I was about to say. So both schemes are affine, so that they are given by the sheaf of OT algebras, and the sheaf corresponding to this one is this sheaf of algebra. So it's the Laurent polynomial ring of O of t, and the structure of Hopf algebra is given by this. Maybe I should have made it clear that it's a parenthetic remark. So this is the Hopf algebra, which corresponds to the group structure on the multiplicative group. And by definition, this one is a relative spectrum of a T of this OT of algebras, where here the commultiplication is given by delta of m is m tensor m, and epsilon of m is 1. So does this answer the question? Okay, so yeah, okay. Okay, so and so there is so obviously ms is inside this, and so the theorem is that we don't have more. And so let me write it here. So the biduality theorem, so the morphism that we just mentioned from this constant group to the dual of the multiplicative group is an isomorphism. Okay, so we are going to prove this this theorem. So proof. So what we have to prove. So let us give an. So consider psi from OT x minus 1 to OT of m, homomorphism of OT of algebras. And so we want to prove it comes from some locally constant function from t into n. So this is what we have to prove. And well, so I give Grothendieck proof, which I think is very nice. After the proof, I will tell you that, well, this fact is well known, at least in the affine case, but the proof is very beautiful. So the first observation is that the sheaf OT itself is a GM module. This is a co-module over this op algebra. By so the co-multiplication that send the coactions that send any function f to f tensor x. And this is so this is a fancy way, so just to say that for any scheme u over t, well, the ring of function of u is a module well, as a natural action well of a GM of u, which is just invertible function. Okay, so and that is a section X in O of U is acted by an invertible section just by the product. Okay, and so this corresponds with this. This corresponds to this comodal structure. But since we have a map of algebra here, then so this together. So this together with the Hoff-map psi makes O of t into d of m t comodule. Or if you prefer, we have a morphism of group schemes here, and GT acts on these coherent sheaves, and so this group act also. So we have a structure of a comodule. Hence, by the previous lecture, hence we have, and so let us call this F. So we have a direct sum decomposition. F is a direct sum of all M in M of a summand corresponding to Fm. And each Fm is locally free OT module, because it's locally a direct summand of a locally free one, and this one is OT itself, so it has a rank 1, and so each summand has to be of rank 0 or 1. So this means that locally all of these are 0 except one of them. And so this gives a partition. Hence, we have a partition. Hence, we have a partition. It's a disjoint sum parameterized by all M of Tm, where on Tm, Fm is equal to OT, and all the other Fm prime are equal to 0. So we have this decomposition. Okay, and on Tm, the coaction of DMT is given. Oh. Is given, so it is given by F that goes to and on this, so any section, any local section F of OT, but on this subset OT is Fm, so it satisfies so this. Okay, so TMF T is just Fm, so which means that this diagonalizable group act by the character M, so which means that we have this. But on the other hand, by definition, how did we get this coaction? It was just derived by this one by replacing. So if we have a Hopf algebra and a map of algebra like this, so the correction is obtained. We just apply psi to whatever we had here. So we had this, and so we obtain. So on Tm, the psi we started with is given by psi of x is M, and so this is what we wanted to prove. So we started with something arbitrary, and we obtain a partition such that psi is given by m, and so which is precisely the isomorphism that we obtain from a locally constant function phi. So this proves the theorem, and okay. Well, so essentially the proof is the computation we made the other day that we have this decomposition. Okay, so the result is also, well, it's also known in algebra. If it's an exercise. So if we look at this Hopf algebra over a ring, over a field, we have to look at the so-called group-like element. And so over a field, it's very easy to see that the group-like elements are just the elements of M. So it's very easy over a domain when there are no zero divisors. Yes, and so this gives a function. Yeah, that is a function. Yeah. So this is a function. Yeah. So this gives phi. Yeah. So this gives phi from t to m. So to every t is sent to the m such that t is in Tm. Okay. Yeah. So we have this. Okay. So well, that's an exercise that one can do in pure algebra, but it's very unpleasant when there are idempotent in the ring, because well, if you write equations, then you end up with an orthogonal system of idempotence, which was exactly the proof we made the other day. So it's good to use the same proof instead of making it again. So we have this very important theorem, this biduality theorem, and which means that we recover the constant group MS from the diagonalizable group D of MS. And for that reason, we call, just introduce the definition. So we call MS the character group of the of MS. So let me make it group scheme. Of D of MS. Okay. So this we'll see that this is a progress from the usual theory, because in the usual theory, when we work over a field, well, we have a diagonalizable group. Well, so we have the abstract group of characters, which is just the set of group homomorphism into the multiplicative group. But here we get more. We get a structure of group scheme, and this will allow us to construct new groups from old ones by Galois descent. Okay, so the next chapter is now what we call twisted constant groups schemes. So we start with the definition. So group scheme E over S is called twisted constant. Twisted constant if every S in S has an affine open neighborhood. Neighborhood, call it U, and well, let us rather write it. If for every S there exists an affine neighborhood and faithfully another a flat surjective map from some other scheme U prime U with U prime affine such that the base change ES prime is isomorphic with MS prime for some, yeah, thank you. U prime is, okay, just to play safe, let me say that twisted constant of type M. So we fix the type, which is our favorite abelian group. Okay, so this is the definition. So after some faithfully flat base change, it becomes constant. And further, one says that E is a quasi isotrivial. If so, let us give a name to that map. Let's call it F. So if F can be chosen etale, let's call it isotrivial if there exists a global map from some S prime to S, which is finite etale surjective. Such that E lifted to S prime is constant. And finally, let us say that it is locally isotrivial, respectively locally trivial. If for any point S in S, there exists an open U such that E restricted to U is isotrivial, respectively trivial. Okay. So it's so these are exactly the same definition as for groups of multiplicative types. There are various notions of local triviality. So
sorry, what is the difference between a group of multiplicative type and a twisted constant group scheme?
they're dual to one to another.
I
will
see.
prove. We will extend the biduality theorem to the larger class in 1 minute.
Okay. Okay. Thank you.
So this was just the baby case to start with.
Okay. Thank you.
Okay. And so since the question just came, so I was planning to give an example, but let me start first the theorem. Yes. Yes. I show you in a minute. I show you, well, yeah, that's also a very good question. I will answer it at the end. Yeah, so locally, isotrivial is very different from quasi-isotrivial. So let me start. There are two propositions and one theorem. So let me write the first proposition. So as you guess, there is a duality between, so let's me write first a proposition, which in the notes is proposition 4.4. So let's E twisted constant over S of type M. Then firstly, so we define we define the dual. It is defined as a functor, but it is in fact representable by a group of multiplicative type. Let us call it H. And which has the same type M. And the second property is that we do have biduality. One has, if we take the dual of H, we recover E. And 3, we have that E is a constant if and only if H is diagonalizable and it is quasi-isotrivial, respectively isotrivial, and so on, if and only if H is so. Okay, so we have a way to go from twisted constant to diagonalizable, and the converse is true. So let H be a group of multiplicative type. Let be an empty group over S of given type M. And here we have to make an extra, we have to assume that it is quasi-isotrivial. This is an extra hypothesis. Grothendieck doesn't know if this is needed or not, but at least if it is quasi-isotrivial, then the functor d of H is represented by a twisted constant group E. We do have biduality, that is the dual of E is H, and 3 is as before. 3 is as in 4. That is, one is constant or quasi-isotrivial if and only if the other is so. And then we have the theorem 4.6. So the functors E goes to D of E, and H goes to D of H, are anti-equivalence of categories between the category of quasi isotrivial twisted constant groups and quasi isotrivial empty groups. Okay, and so well, let's specify the type. And 2 is the same statement, same with isotrivial, locally isotrivial, and so on. Okay. And so the proof could be given in another lecture because it uses the theory of faithfully flat descent. But let me finish with let me try to answer the question by Professor Balaji, because it's an important question. And so this is something that I had prepared for the lecture of next week, but I will give it right now because I think it's a very interesting example. And so this example is the mother of descent theory. So for this statement, you can look in SDA 1 and of expose 1, because there Grothendieck considers this example, and he said that that was the example that led him to the theory of descent theory. So this is really the mother of everything. And so the example is so consider a nodal cubic. That is well, like this, which has a double point, and so the normalization is just A1. Oh, so so that one is obtained by gluing 2 points. So let us call this this cubic S, and so now if we consider 2 copies of A1 with the point 1, 0, and 1 here, and we glue, so we take another copy of A1 and we glue them together. So this is 0 and 1, and we glue it with another copy of A1, But now, so this point here, it's a 0 of the other copy. It is the 1 of the other copy. Okay, so there is a natural projection to this curve, and this map is etale. With Galois group Z over 2Z, because if you swap these two copies, these 2 points are swapped, and yeah. So I forgot to say. So this is so this nodal cubic is the same as A1, where you identify these 2 points. So if you identify these 2 points, so this means that the ring of function of this is just the polynomials which take the same value at 0 and 1. Okay, and so this is the ring of the nodal cubic. Okay, so this map is etale, and if you remove one point, it remains etale. And now that you know that this one is etale, then you can glue several copies together. That is, you can form this. We have 0, 1, and now we glue another copy with 0, 1, and we make another one, 0, 1, 0, 1, and also the other way around. So this is 1, 0, 1, 0. And so you keep going in both directions, and you call the resulting thing P. And so you have a natural projection from that P onto the curve you started with. And so you see that the P is the principal Z bundle over S. Okay, because, well, obviously Z acts by shifting the copies, and we are going to use this to construct a group of multiplicative type, which is quasi-isotrivial, but not locally isotrivial. Okay, so we see that the map P2S is etale, but well, it's not affine, it's not quasi-compact, because the inverse image of a point in the base is isomorphic with Z. It's etale, but not finite etale. Okay, and so we can consider the two-dimensional torus of this P, and so this is the dual group of Z2 over P, and we know that the automorphism group of Z2, so this is just a GL of Z2, and there is a map from the group Z to this group, so just send the integer n to the matrix, this unipotent matrix. So we have this Galois group. Well, it's infinite, but it's the group of the bundle. So it's acting on this. And so using this, so we can construct. We can, so we obtain an action of Z on this group. With Z acting on both E and okay, so it's as a case I mentioned previously in the affine case with a finite group. It's a bit more difficult. I do not want to write things because P is not affine, and actually there is no affine subscheme which is fixed by the Z action. But morally, I hope you will agree that there has to be such an action of this torus, where P is acting, Z is acting on P in the natural way, and it's also acting on the multiplicative group by switching by this thing. Okay, and now this so this one is still affine over P, and by a result that we'll explain next time, so one can descend. Well, we need some descent, something here, but let's say it's a proposition. So there exists a multiplicative type group H over S such that H P is isomorphic with G and P2. So H is quasi isotrivial, but not isotrivial in any neighborhood of the singular point. Okay, so let me try to explain this. Well, so one has to prove that this descent, but so there is a result of Grothendieck about the descent for a fine scheme. So we will come back to this later. So there is this, one obtains a group of multiplicative type. It is quasi-isotrivial because when we extend the base from S to P, it becomes trivial. And so here we have this curve with this singular point here. So actually, we can see that this H, it is actually trivial if you remove the singular point, because over the singular point, you have a disjoint copy of A1 and -2 points, and everything is trivial. But one can prove that in no neighborhood of the singular point, this becomes trivial. And here we need so there is another result of Grothendieck when he considers this example. He proves that any finite etale covering, Galois covering of these curves come from this one by reduction modulo n. Well, of course, so you have this Z bundle. If you, from this, you can construct a Z over N Z bundle. And Grothendieck proves that any Galois covering of this comes such a Z over NZ model. So this infinite thing is universal for the Galois covering of this. And you see that over no such quotients of P, the group of multiplicative type we are talking about, it never becomes trivial, because if it would, then the corresponding action of the character group would be trivial. But you see here the matrix 1, 1, 1 has infinite order. So it does not become the trivial action of any n. So this is the difference between quasi-isotrivial, means that there exists an etale map, possibly a fancy one and not finite, that makes the thing trivial. And locally isotrivial means that, well, locally you can trivialize with a nice finite etale Galois extension. So this example is very interesting, and so this occurs only because there is a singular point. So I hope to prove later, anyhow it's in SGA3, that if the base is locally noetherian and normal, and even geometrically unibranch suffices, which means that the normalization is bijective, then any group of multiplicative type is isotrivial. Okay, so this never occurs in the smooth world. Okay, and I will stop here so that you can take your bus, and tomorrow, so we start at 3:15 tomorrow. Okay. This is okay. I'm not sure.